Good morning and welcome to Webinar 2 in the Building Smart program. Today we'll be talking about general building science and energy efficiency design theory. This program is brought to you jointly by Consumers Energy and DTE Energy, the state's two biggest investor-owned utilities. Founded in 1886, Consumers Energy provides natural gas and electricity to 67% of Michigan's residents. The older of the two utilities, DTE Energy, was founded in 1849, and it provides electricity to 2.3 million customers in Southeast Michigan and 1.3 million gas customers across the state, including the Upper Peninsula. Since 2019, these two utilities have led the charge in Michigan towards sustainability and energy waste reduction programs and rebates. Their efforts recently led to Michigan tying with California for the #1 ranking of utility public benefits programs in the state energy efficiency scorecard. My name is Sonia Ponce, and I will be your facilitator for today's webinar. It is raining where I am, and I tend to have connectivity issues, so I'm going to turn off my camera throughout for the bulk of the presentation just to save bandwidth, and then I'll turn it back on at the end of the series for Q&A. And I apologize, John, I forgot to keep saying next slide. Hopefully you've been keeping up with me. I don't see the slides on screen.
Uh-oh.
So I'm not sure that you're sharing yet.
Let me see here. Apologies. It should be good to go now.
Yep, we're good to go, and you're on the right slide. Slide number 4. Awesome. All right, so again, I'm going to go ahead and turn my camera off to save bandwidth, and we will get going. So next slide here. So today we're, over the next several weeks, we're going to be looking at high performance homes. And today we're going to be laying the foundation for that work. We're going to have a conversation about really how buildings work and take a closer look at some of the primary systems that comprise modern residential buildings. Then we'll wrap up with a brief look at the role that maintenance plays in buildings and their energy performance. Next slide. What we hope that you will get out of this seminar today is that you'll be able to define building science and have meaningful discussions about building energy performance and some of the factors that influence it, as well as those that impact our health and comfort. Since according to the time use survey by the U.S. Bureau of Labor Statistics, we spend about 15 to 18 hours per day at home. That's up from about 12 hours that we spent pre-pandemic. And it seems as though with the ability to work from home, those hours are likely to not go back down to that 12 mark. All right. So next slide. The human body is a machine. It performs a number of amazing functions, one of which is to maintain its own comfort while we deal with the changing environmental conditions around us. And we consume energy in the way of food, and we burn that food as fuel to perform the everyday activities that we do. And depending on the activity, more or less waste heat is generated. For example, sitting in your seats watching this webinar, you are likely generating about 350 BTUs per hour per person, or 1 MET, or metabolic unit of energy. If you were exercising, you might produce about 1,300 BTUs per hour, or 3.5 METs. Deep inside our brains, our hypothalamus is controlling the various physiological processes like blood flow to our skin and shivering, sweating, things like that, to help regulate, to help maintain our body temperature. In addition to giving off heat, the body also exchanges gases and vapor with the external environment. Through respiration, we exchange sensible and latent heat through convection and evaporation. We take in air at ambient conditions and about 21% oxygen, and we expel or expire that air at nearly saturated conditions, not too far from our core temperature, but the oxygen content is about 16.5%. So we've added about, or we've exchanged that oxygen and we've replaced a portion of it with about 4.5% CO2. Right, our cells are using that oxygen to release the energy we need, and CO2 is the byproduct of that internal combustion that's taking place inside of us. Next slide. Very similar to the human body, right? The buildings in which we spend most of our time also exchange heat, air, and moisture with the outdoor environment. Our homes have heating equipment that may burn fuels to maintain comfort conditions, similar to the way that we burn fuel. And just like our breathing in oxygen rich air and expelling used air with higher CO2 content, buildings have ventilation systems that bring in outdoor air and push out used or stale air in order to improve indoor air quality. Right? This exchange helps maintain air cleanliness and get rid of moisture and odors and things like that. So today we're going to take a deeper look at the systems that perform this important work of maintaining our comfortable and healthy indoor environments. Next slide. And at the same time, we'll be talking, as we're talking about the building systems, we'll also be talking about how effectively, they do this work. So when we talk about building performance, what is that? Building performance is the sum of a variety of metrics that we use to evaluate how well buildings perform their essential functions, the functions that we ask of them. One of the most important metrics is energy consumption. How much energy do our homes require to provide us with a comfortable indoor environment? But other metrics matter too, such as indoor air quality in terms of air cleanliness, relative humidity, odor levels, mean radiant temperatures. We can evaluate homes in terms of anything we want: usability, physical comfort, aesthetics, any number of criteria. When we take the sum of all of those metrics, right, that we want to consider, and we rate them and we rank them and combine them into a single value, that then represents the overall performance of the house or the building. And that value could be a letter grade as shown here, or it could be a number from 1 to 0, as in the home energy rating system or HERS index. Next slide. Any conversation that we have about the home as a building inevitably is going to make its way around to the subject of building science, right? The study of how building systems interact, the exchanges of energy, air, and moisture that take place between the building structure, its systems and equipment, and the object and also the people inside of it, as well as exchanges with the outdoor environment. A lot of recent conversations about building sciences have been kind of focusing on more so on ventilation and air exchanges than on HVAC, for example, the heating and cooling of the facility. But all of these considerations matter. They all work together to determine the indoor environment and whether we find it satisfactory or not. Next slide. So the outdoor environment that our buildings are contending with originates from the Earth's revolving around the sun, as well as the Earth's tilt as it revolves. Although it looks like the sun is in the middle of the Earth's elliptical path, it's actually closest to the sun at the winter solstice. Right? That's when we receive the most solar energy, about 445 BTUs per hour per square foot of space. At the summer solstice, right, we're receiving about 415 BTUs. And as the Earth moves around the sun, different parts of it get more or less direct sunlight, resulting in various temperatures and lengths of days. etc., that are responsible for our seasons. Next slide. The Earth's revolution is also a driving factor in the water cycle, the way water moves around the planet, the way the Earth recycles water, right? So as the sun's radiant energy falls on the Earth, it heats the ground, and through conduction causes molecules of water within the ground within the Earth to warm and rise to the surface, where they may turn to steam and evaporate. The sun also heats bodies of water, rivers, oceans, lakes, etc., more directly, so much so that molecules of water turn to steam and evaporate from them as well. We also have pressure and temperature differentials that are caused by the sun unevenly heating up the earth and the air, right? And we know that warm air is less dense, so it rises, cool air, which is more dense, falls. And this motion combined with the earth's rotation, which is faster at the equator than at the poles, results in wind, right? That fast moving air that also can pick up moisture from the surface of the earth and the surface of bodies of water and carry them away in a process that we call convection, right? And mass transport. Some of that water vapor, right, once it's in the air, right, it may come in contact with cooler air and give up its heat. It may then condense back into a form of precipitation, rain, sleet, snow, hail, depending on what the weather conditions might be. Next slide. So now let's take a look at how all of this impacts our homes, starting with the building envelope, right? The walls, the windows, the doors, the foundation, these parts of the home that form the barrier separating the inside from the outside. Next slide. So geographically, the planet is divided into climate zones, which are areas with similar and consistent weather patterns. There are 9 thermal zones from the South Pole to the North Pole, and they depend on how many heating degree days an area may have. Degree days, or heating degree days in particular, are simply the multiple of how many days the average temperature is below the threshold at which heating is required by the building, multiplied by how many degrees it is below that threshold. And this gives us an idea of how much relative heating may be required for buildings in one location compared to another. Locations with higher heating degree days generally require more heating. The land here in Michigan, the state falls into 3 of those thermal zones. So the thermal zones are numbered from 0 to 8, with the higher number being colder climates. And so you can see that the lower peninsula has moderate climates, climate zones 5 and 6, and the upper peninsula is relatively colder with climate zone number 7. There are also 3 moisture zones across the planet. These are marine, moist, and dry. And all of Michigan falls into moisture zone A, which means that we're not dry and we're not marine. We're somewhere in the middle. We are in that area that zone called moist. Next slide. So since we have a moderate to cooler climate here, we design our building envelopes to help protect us from primarily colder temperatures in the winter, which this is Michigan. We experience that for quite a bit of the year. We put thicker insulation in our walls. We have code mandated maximums for the amount of thermal conduction that we allow through those walls, as well as through doors, windows, roofs, and floors. Next slide. We design our homes so that we can enjoy the sunlight and the warmth of the summer, but so that they also protect us from those seasonal winds and winter storms that we get here. Next slide. Now, heat flows from warmer temperatures to cooler temperatures, and nothing stops that process. But thermal insulation can significantly slow it down. And that, combined with regularly adding heat to the house, as with a furnace or boiler or heat pump, can get us to a point of comfort where we don't even notice that flow of heat out of the house, right? So the insulative property that we're talking about is called conductance, and it's the rate of heat flow through 1 square foot of material, typically 1 inch thick, when there is a temperature differential of just 1 degree on either side of the material. Now, we want this number, this conductance, to be as low as practical. Right? The inverse of conductance is thermal resistance. We typically call this the R value. And we want that number to be as high as practical. Next slide. So here's kind of what the flow of heat looks like as it conducts through the wall, right? We can see the sunlight falls on the wall and a small portion of the heat is reflected back to the outside, but some of it makes its way through that wall, right? Through the insulation, through to the inner wall, through all the way to the occupied indoor space. Next slide. The rate at which that heat travels is defined, right, by the U value of the wall assembly, by the area of the wall, and by the temperature differential, right? That difference between the inside and outside temperatures. And note that temperature differential could be positive or negative. So heat, depending on your point of view, if our point of view is from the inside of the house, heat could be flowing in or out depending on the season and the conditions outside, right? So in the wintertime, we're concerned about losing heat out of the house, right? We want to try to keep it in. In the summertime, we're concerned with getting excess heat out of the house, right? Keeping the indoor environment cool. Next slide. Here are just some representative R values of some common building materials. And we can see, for example, that brick has an R value of 0.20 per inch, right? And the units of the R value are at the top here, right? So again, that's the inverse of the U value. And so the units are hours, foot squared per differential degree, divided by BTUs. And the numeric value for the brick is 0.2 per inch. If we look at the polyurethane foam board, that has an R value of 6.25, same units per inch of thickness. So that means inch per inch, right? A wall with foam would have a heat transfer rate 30 times slower, right, than the wall of brick alone. And that's the value of adding the insulation. It doesn't stop the heat flow, but it just slows it down tremendously. Next slide. Now, the wall assembly U value or R value, whichever one we're considering, again, one is the inverse of the other. But we arrive at these values by adding up the U value or the R values of the constituent layers, because the wall is made up in layers of material, right? But it's not that straightforward because the insulation is not continuous. In some areas of the wall, the insulation is interrupted by studs, which have a lower thermal resistance. So we have to take that into consideration. Next slide. So when we consider the heat flow through the various pathways, right, one with just insulation materials and one through the studs, we see that we come up with some different R values for those two paths. And to determine the R value for the wall, right, we first have to look at those individual paths that make up the wall. So we see here that both paths have pretty much similar materials, all of the same materials, except that path 1 has the studs and path 2 contains the insulation, right? The bulk of the insulation. There are insulative materials in path 1 as well, but the bulk of the insulation that's added to the system specifically to slow down that heat transfer, that we find in path 2. Next slide. And so then we take an area weighted average of the value for those two paths. We come up with an average U value for the wall. And then of course the inverse of that is the R value for that wall. And it's important when we're evaluating these numbers or developing these numbers that we consider those two paths because they do have a significant impact on the thermal resistance of the overall envelope. Next slide. When we have glazed building elements, our windows, our doors, our skylights, doors with glass in them, right, or glazing in them, and skylights, these are handled similarly to the wall, but they also have some additional metrics, right? Because they have a glazing, because they're letting in daylight, and the heat that also comes along with that. These have the added metric of solar heat gain coefficients, right? How much solar heat is primarily through conduction and radiation comes through that glazed material, right? But the units of it are just as they are with the walls. Next slide. Here we can see that the heat transfer through a multi-pane window also takes more than one path, just like it does through the doors, right? And I'm sorry, through the wall. And just like through the wall, some of the solar energy is reflected. Some of it makes its way through the window glazing and through the frame. This is an example of a thermally broken window. So it's got a non-metallic material in the framing that further reduces, right, slows down that rate of heat transfer. But otherwise, it's very similar to what we see with the wall. Next slide. Next slide, please. And so as we're, oh, okay. And so as we are evaluating or determining the overall U value for that window, we handle it very similarly to what we do with the doors. So we look at the glazing material, the glass inside the window assembly, and the area of that. We also look at the U value for the framing material, whether that be wood or some metal or some vinyl, and the area of that frame. And then we also look at that edge along the glazing frame border, right? That has a unique thermal performance characteristic. And we look at the length there, right? Next slide. Windows also, because they are intended to allow in visible solar energy, they have another factor that we're interested in, and that is their visible transmittance, or VT. And this is how much light makes it through. So we've previously been talking about how much heat makes it through. Light is energy as well, and that comes through very similarly to the way the heat comes in. Right. Some of that is reflected, some of it is absorbed by the glazing material, heating it up, right? And some of it makes it through that material into the occupied space. Next slide. So often we want windows, to let in as much light as is possible, but only in, light energy, but only in that visible spectrum where we don't want the additional heat. So we want to have the daylight without adding that extra heat into the space. So to mitigate that, we might apply films, low E coatings, next slide, or we may add additional panes of glazing, or we may color, tint, or frost the glazing to make it more or less transparent. Right? Next slide. In addition to the heat and light transmissions, when we consider windows and doors, these are the components that interrupt the wall's thermal barrier and that are often meant to be operable, right? So we have to also consider air leakage. Nothing that's meant to open and close can be totally sealed off 100% airtight, right? But we can get kind of close, right? So there's always going to be some measure of airflow across that boundary. And air leakage, right, the rate of airflow across that boundary is how we determine or how we evaluate that metric. Next slide. So when we're selecting windows for our homes, right, we want to make sure that we consider air leakage as well. Right? Windows will bear a manufacturer's rating label that has all of these characteristics listed: its U factor, its solar heat gain coefficient, its visible transmittance, and its air leakage. Right? This label indicates that it's been tested in accordance with the test criteria of the National Fenestration Rating Council. High performance windows will have additional labels. So, for example, this particular image here is an example of an Energy Star rated window. Energy Star products are required to be, in order to obtain an Energy Star label, products are required to be between 10 and sometimes, 30, 40, maybe 50%, or even higher, more efficient than baseline products. And so you can see here that this window would clearly state what its performance characteristics are. Next slide. Next, okay, perfect. And so we see here that for doors, we have a similar rating, right? We have a similar label. This gives their performance characteristics. It gives the U factor, and it gives the solar heat gain coefficient for doors that are glazed. If there's no glazing, there wouldn't be that solar heat gain coefficient here. But you can also see that at the bottom, they also have an air leakage rating for the doors as well. Next slide. So here in Michigan, we have minimal thermal performance criteria for the various parts of the building thermal envelope, minimum allowable window R values, door R values. These are not the same necessarily as the wall R values, right? They have different criteria, but they all have minimum values. And also those values, for example, that are required in Oakland County, which is in climate zone 5A, are not the same as those that are required in Marquette, which is in climate zone 7. Right? But each component of the building envelope has minimum performance criteria. Next slide. But those minimum, those mandated minimums, they are just that, right? Minimum performance values. We always have the option of building better to, for example, use dynamic glazing that can change optical properties. So if we want to have a window that will change its transmission, or change the amount of light or heat that it allows to transmit, we have dynamic glazing for that. We can always add, better trusses, right, that allow us to increase the amount of insulation that we're able to provide for the roof, right, of our facilities. We can use insulated structural panels, right, that provide better insulation in a smaller footprint. Sometimes they're thicker, but sometimes they're when they've been engineered to be insulated panels, they do tend to be a little bit thinner. We can also use advanced framing and construction methods, right? Again, the thermally broken windows, triple pane windows, windows with inert gases between the panes. There are a number of things that we can do to make our facilities, to make the envelope of the facilities more efficient, more effective, more high performing. Next slide. But of course, whenever we do, we want to make sure that we have a fully developed, a well-developed air barrier that is able to pass the envelope air leakage test, right? So we want to have a tight envelope for the building, and we measure that tightness by doing an air leakage test, right? So we want to do things like making sure that we've sealed up wall outlets, right? So we can put some gasketing behind them to make sure that we don't have air leakage there. We want to make sure that we've got sufficient caulk around our windows. We want to make sure that there's sufficient contact with our floor insulation, whether it's specifically in crawl spaces. We want to make sure that we've sealed, with foam or caulk or whatever, all of the mechanical, plumbing, piping for HVAC, penetrations to the building envelope. Right. Next slide. High performance homes consider all of the spaces or places in a home where leaks might occur. And they take proactive measures to help reduce that leakage to minimum values. So we're looking at the entire facility. Again, every penetration of that air barrier to see where might leaks occur. Next slide. And that air leakage test, we want to make sure that that is something that's a criteria that is passed, right? So homes here in Michigan must be leak tested, and they must pass that test, right? The criteria is maybe a little liberal, right? The minimum criteria is 4 air changes per hour at 50 pascals. However, high performance homes, right, have significantly less leakage. They are much tighter. They have a much tighter envelope, right? And we can see here that high performance homes might have an air leakage rate of 0.6 air changes per hour at 50 pascals. Next slide. So I think, yep, I was going to say, I think we're skipping the polls. We didn't quite get those together today. So we're going to move into HVAC systems and take a look at those. Let's see how they help keep the indoor environment at desirable conditions inside the home. So next slide. Human comfort is defined by a number of factors. We've talked about how the building envelope helps protect us from outside weather. But even within the indoor environment, there are factors that impact our perception of comfort, right? So airflow rate and air quality, whether the air has a smell to it, an odor to it, right? That's why we open windows, for example, when we may be cooking. Right? Humidity, the moisture level of the air, you know, impacts our ability to, for example, to sweat, to have the sweat radiate, to have the sweat evaporate from our skin and cool us down. So if it's too humid, right, we tend to be uncomfortable. We're also concerned with, or one of the other factors is the insulative value of our clothing. So just like buildings have insulation put into the walls, our clothing has an insulative value to it, right? The units of clothing insulation are called clothes, not CLOTHES, but CLOS, a clo, right? And, we naturally wear heavier clothing in the winter, lighter clothing in the summer. We we innately understand the value and the concept of insulation. And then also our comfort is impacted by our activity level, what we're doing in the home, right? Okay, next slide. And it's important to recall that the building envelope, while it certainly is that first line of defense, that barrier from what's going on outside, it does not provide the indoor the comfortable indoor environment alone, right? It works in conjunction with the other systems. And so one of the primary systems for us here in Michigan is heating. And heating can take a number of different forms. This is just some images of a boiler heating system that would be used during the cooler months of the year. This is a traditional system that's using boilers. They distribute either steam or hot water around the facility. Then there are radiators that are radiating that heat out into the space. That radiated heat actually warms up objects in the room that re-radiate that, and we end up with a nice, warm, cozy environment. Next slide. Rather than heating water, right, furnaces heat air and circulate that through ductwork. Some of the benefits of using a furnace rather than a boiler system are lower upfront cost, faster heating because you're not having to heat the entire um, um, radiative system, right, before heat can be distributed out into the space with a boiler. All of the radiators, all of the piping, all of that has to be warm, right, and then the boiler system will radiate heat out into the space. Right, with the furnace, you're just heating the air directly and putting that warm air into the space. So you don't have to have the ductwork doesn't necessarily have to be warm first, and you don't have the facility itself, the structure of the facility isn't warm and radiating that. Right, you're just putting that warm air out there. So you get faster performance there. Also, you get less risk of water damage, right? With the boiler system, you could potentially have leaks in various places, and you may not see that in the walls until you see, water damage, right? So you don't know that there's a leak until you actually see the water damage. With heated air or conditioned air, you don't have that risk. And then also, heating systems with forced air integrate well with cooling systems as well. We'll talk about that in a second here. The next slide. There are other types of heating systems as well, right, that are still offered. Electric resistance heating. This is kind of expensive and not used often, but it is. We still do see it applied in additions, for example, to existing facilities because it's simple and easy to install. Up north, we tend to, particularly in the UP, we may see wood and pellet boilers and furnaces. These are more environmentally friendly than some of the other some other fuel sources, and they also provide backup power in the event of an outage. Right, you don't necessarily need utility service to operate a pellet or wood burning furnace. You've got your fuel there, stored at your house with you. We mentioned earlier that that furnaces are really great for integrating with cooling systems. Next slide, please. So a central air system is a system that uses the existing furnace as an air handler, right? So the furnace has a fan in it, it's got that blower wheel, and it's already, typically the furnace would be heating the air and then blowing that throughout the space through the ductwork. When you add a cooling system to that, when you add central cooling, you add a cooling coil to that furnace, right? So you turn off the gas, you turn off the heating portion of the furnace, and you allow that cooling coil to cool the air, and then you send that out to the space. Right, so this added equipment would include that evaporator coil that goes on the furnace, as well as an outdoor unit. That outdoor unit could be a traditional condensing unit that does cooling only, or it could also be a heat pump that provides heating and cooling. And that way you would have a little bit of redundancy, you would have a dual fuel system. So you could, for example, use heat pumps. Here in Michigan, you definitely want to make sure that you have a low temperature heat pump, but you want to make sure that, but you could use a heat pump to provide heating for, to as low as the heat pump could go. And then you could switch over to, for example, natural gas or whatever other fuel you may be using for that furnace. Next slide. Heating and cooling systems. You can also do cooling with window air conditioners. These just go straight in the window, and you don't have to deal with ductwork. They cool a specific space, right? We also have ductless split systems where you have an indoor unit and an outdoor unit. Again, with no ductwork, so these are really flexible and great additions to existing facilities or upgrades to existing facilities. Next slide. We talked a little bit about heat pumps. Those ductless splits can be heat pump units, and that outdoor unit that you pair with a furnace can also be a heat pump. Just a little bit about heat pumps. They have a reversible refrigeration cycle. So the traditional cycle, you have your evaporator, your condenser, your compressor, which raises the temperature and pressure of your refrigerant, right? Goes through the condenser where the refrigerant exchanges its heat with the outdoor environment. So the refrigerant cools down, comes back to the evaporator, and then gives off its heat to the air going across the evaporator that then goes out into the space. With a heat pump, this cycle is actually reversible. So we don't have a dedicated evaporator and a condenser. What we have are indoor and outdoor coils that can do double duty. So the indoor coil can be the evaporator or the condenser, depending on what the situation calls for. Next slide. High performance homes might also use advanced. Oh, I'm a little bit behind on the slides here. But high performance homes can also use advanced HVAC systems. So you might, for example, see a radiant floor heating system or a geothermal system. These type of systems are more efficient. They result in lower utility bills, and they can reduce, particularly the radiant floor system, can help reduce the presence of ducts and allergens and things like that in the home. They also reduce the noise a little bit too, so you don't hear the systems starting and stopping as much. Geothermal systems, these systems capitalize on the Earth's consistent temperature, and they use that as a heat sink or heat source to cool and heat our buildings. So they extract heat from the ground in the winter and transfer it indoors. And during the summertime, they extract heat from indoors and transfer it to the ground, right? And both of these systems are more sustainable, more environmentally friendly. And they also, although they have slightly higher upfront costs, they have lower lifetime costs because of their greater efficiency, lower energy bills, and they provide increased comfort as well. Next slide. Some of the ancillary equipment that we see with HVAC systems helps to improve the indoor environment, provide better indoor air quality, right? So we've got cleaning components, we've got filters, air cleaners, things like that. Of course, these need to be maintained. They need to be changed on a regular basis, looked at. We'll talk about maintenance a little bit later. But we also have humidity control equipment that helps to maintain humidity levels within the comfort zone that we want, right? Typically, we like for humidity levels to be around 50%. That is, the percentage level where humans find it most comfortable, and actually it is where viruses and other bacteria have a difficult time surviving. We're a little challenged here in Michigan in the winters to try to keep humidity levels that high. So they may range from as low as 20% to that 45% mark or 30% mark in the wintertime. It's difficult to maintain the higher levels, but we do want to try to do that. We've learned through COVID the importance of humidity and the role that it can play in not just our comfort, but our health. Next slide. The HVAC system also consists of ventilation. We have learned recently through a number of studies that, for example, cooking indoors without good ventilation can result in poor health, right? It can cause respiratory issues, it can cause headaches, it doesn't cause asthma, but it can exacerbate things like asthma and COPD. Cooking also generates moisture, which if not removed can lead to mold or mildew growth in the house, which further negatively impacts indoor air quality and can cause potential allergies. Right, so we can either naturally ventilate spaces by opening windows, which we have traditionally done, or we can mechanically ventilate spaces with fans and energy recovery ventilators, which we do. So, it's recommended that we have, vents over our cooking ranges to extract that moisture and extract those fumes and particulate and smoke from cooking. Most homes in Michigan, the older homes in Michigan, have ventilation fans right in the kitchen, and some have them in the bathroom as well. But most fans definitely have them. I live in an older home in Michigan, and so I know that the neighborhood is full of these little kitchen fans. But today we see builders installing energy recovery ventilators that can not only exchange outdoor air for indoor air, they can actually extract energy from those two air streams and exchange them, reducing the amount of energy that we need to use electricity to condition that air. Next slide. And of course, whenever you've got a system, you've got to have some sort of control, some sort of way of maintaining control of the system. And so with the HVAC system, we do that with thermostats. And those thermostats can be many older thermostats are just manual thermostats. You set them and that's the temperature. But over the years, those have been replaced with electric, digital, and now smart thermostats that can sense occupant behavior, tell whether or not you're in the space, and can help monitor and manage temperatures for various spaces in the home. So if, for example, everybody's downstairs having dinner or in the den watching TV after dinner, we can make sure that the downstairs level is a little bit more comfortable, and the upstairs temperature cannot be allowed to float a little bit if nobody is upstairs doing anything, and then vice versa when occupants change spaces throughout the home. Next slide. With HVAC equipment, it's important. One of the important things here. So with the building envelope, you're concerned with R values and U values, and you want to make sure that you've got high R values, and you want to make sure that you've got a well sealed or a tight air barrier, right? With HVAC equipment, we're concerned with the size or the capacity of that equipment. We want to make sure that it is properly sized, not oversized, not undersized. Sometimes we may think that bigger is better, and so we might want to oversize our equipment. But oversized equipment cycles more, it doesn't last as long, and it's not as efficient. It may not be able to unload to the point where its capacity matches the demand from the facility. So we want to make sure that our equipment is sized, and high-performing buildings are properly sized so that they can achieve those comfortable indoor conditions, namely temperature and humidity. They also save on initial operating costs because they're not oversized, and they save on operating costs, right? Because they're more efficient. Next slide. Now let's take a look at the domestic water system. So next slide. So domestic water in the home is used for a number of purposes: for cleaning, for drinking, for cooking, for bathing, for hygiene, as well as for sanitation. Next slide. When we think about the building system and the hot water system, right, that is primarily for the bathing, for sanitation, for things like dishwashing and cleaning and things of that nature. And so water heaters take on a number of forms, just like HVAC systems can take on a number of forms. They can either be gas or electrically powered. They can have an integral storage tank, or they can be on demand, as newer technologies provide. Next slide. We also have heat pump water heaters. These operate just similar to a heat pump HVAC system, right? And they have the benefit of increased energy efficiency. They maximize the energy savings, right, as opposed to using gas or electricity to heat the air, to heat the water, excuse me, directly. These extract thermal energy from the environment they find themselves in. So here in the basement, you have this unit. It is extracting thermal energy from that basement air and using that, putting that into the water to heat the water. Right. So these are extremely efficient pieces of equipment, newer technology that we're finding to be valuable in high performance homes. We also have, next slide, solar water heating systems where we can use the sun's energy directly to heat the water. Um, there are a couple of different types of solar systems. They can either be passive or active. They can have circulatory systems or not. But here you're using that solar energy in place of grid-based energy to provide the heating for that hot water. Next slide. Next slide. Lighting systems also impact energy use, and high performance homes use high performance lighting systems. So with a high performance home, you will see the LED technologies integrated into the home. You'll see them integrated into some of the fixed lighting fixtures that you see in the homes. They'll have controls such as dimmer switches and occupancy-based controls that that respond to occupant behavior. They'll have things like remote controls. They can be managed from a cell phone. Next slide. And they will also incorporate daylighting, right? So this is a free source of lighting in the home. And so you'll see skylights and floor to ceiling windows that allow us to use natural daylight whenever it's available to offset the electricity that we need to light our homes. Next slide. And last, let's talk a little bit about maintenance. So high performance homes have owners that have been adequately trained and prepared to maintain their homes. They understand how the home works. They understand how the equipment works and what is required to maintain the equipment. They have a team and know who they can call for service work. And they have a written schedule of activities, right? Maintenance tasks that need to be done around the facility to make sure that things are operating properly. And when owners are prepared in this way, right, this improves the indoor air quality of the house. It helps equipment to last longer. It reduces the overall cost of ownership, and it reduces emissions, right? And owners are then more satisfied with their homes, right? They're more comfortable there. Next slide. And with that, we've got just a few minutes here for questions. And while we're going to open the floor for questions, we're going to go ahead and just show that next slide so that we can know when the next session will be taking place, which is next Tuesday at 11 a.m. Here's the link if you would like to register for that. If you've already registered for the entire series, then you're good. But some of you may have just registered for just this session today. And next week, we'll be talking about minimum good designs. We'll be talking about that baseline level. Today, we kind of talked about, the systems and things that go into the building. Next week, we'll talk about what some of the values for those R values might be, and things like that. So with that, I'm going to see if there are any questions. John, do we have any?
I do not see any coming in yet. I'll give it a few minutes here, see if people would like to drop their questions in chat.
Okay.
Otherwise, yeah, you've wrapped it up nicely. Hope folks can join us for the next few sessions here. So these are going basically every Tuesday, a few breaks here and there, but almost till the end of the year. So a lot of good information upcoming, and I hope folks can join us for as many of these as they can.
Absolutely. Absolutely.
And since I'm not seeing anything coming in the questions. I guess we can cut loose maybe about 5 minutes early here, and we can see you hopefully all next week at the same time.
All right. Thank you all so much for attending today's session. We look forward to seeing you next week again at 11 a.m. We'll be talking about minimum good design. And have a great day.
Thanks, Sonia. Bye, everyone.